Hello, and welcome to Grakn Orbit 2021. We're here live in central London at Studio 3B, and James, honestly, I feel like we blinked in the last year, flew by.
It's been so fast, hasn't it? And the momentum we've seen in the community in the last year has been just amazing. The number of new projects we've seen coming out, just the sheer work output and work ethic of people, particularly in the circumstances of the last year, just pushing
beyond inspiring, absolutely beyond inspiring. And we are so grateful for everyone joining across the world for the next 2 days, which we feel is going to be both inspirational. You're going to find all sessions covering a range of topics from the community.
We really have fun for all the family. We've got sessions from Grakn 2.0, knowledge, architecture, robotics, causality, neural networks, you name it. As long as your family has a certain demographic, we've got something for you and your family, right?
Absolutely, absolutely. James, I don't know about you, but I think we're ready to go.
Let's do it.
Let's go.
Dennis Verdoliak. I'm a data scientist at Cisco, and I'm also a data science instructor at Santa Clara University.
My name is Suyog. I am lead research data scientist at Dunambi.
Hi, my name is Zepide. I'm Master of Science student of Information Technology in Iran. And for now, I'm working on cancer pathways for my thesis.
Hello, my name is Gunnar Kleeman. I run Austin Capital Data.
Hi, I'm Harvey, a co-founder at Atomic Search, and we're a semantic web startup building the best search engine ever.
Hi, my name is Audrey Bercon, and I'm a researcher at the University of Strathclyde based in Glasgow, Scotland. Today, we are using it to build, with the European Space Agency, a large knowledge graph that will contain the design of several space missions.
My name is Brendan Ferguson. I'm the founder of Source++, which is an open source programming assistant. I think I'm just excited to finally let people know about what a possible future in software development could be like.
I'm Fika, I'm working at TNO, and I work mostly with deep learning and currently combining it with knowledge.
I'm a software developer, and from when I was very, very little, I always dreamed about developing crazy ideas, making them a reality.
At Data Spartan, we build apply AI tools in different areas. On this journey, working with the community has been great, and this community has been the most transparent and responsive I have seen.
It's been invaluable to be part of the community. It's a warm place where people help each other, and it's been really great to be able to get direct feedback and help from members of the core team.
The community, which is just as passionate about rendering complicated and nuanced deep tech data domains usable as we are.
Its helpfulness and creativity, which genuinely inspires me each time.
Hello everyone, good afternoon for everyone who's in Europe, and good morning everyone in San Francisco in America, and I suppose it's already pretty late for everyone in Asia right now. This is a really exciting moment. We've been looking forward to this moment for a very long time right now, and I must say, like, this is my first talk being presented virtually, so I've had the fortune or misfortune, depending on how you consider it, to not have to do a presentation over the internet for the past year, so I'm not gonna lie, I'm a bit nervous, but that is trumped by the excitement of Grakn Orbit that we've all been really looking forward to. It's a shame that we can't meet everyone in the community in person this year, but I know the time will come soon where we'll all be able to get together again. And for now, we're going to be sharing all of our work since last year, since Cosmos actually, virtually right now. And so we hope everyone's excited about all of that. Ultimately, what we're going to be sharing today is our entire journey from last year from Grakn Cosmos and the outcome of it all, the evolution that it has given to our work, to the technology, to Grakn, and to our company. and it's all going to be laid out in this talk, and the team will further elaborate on some of the critical components throughout the different talks on Reasoner and Grakn cluster and KGCN. And so I hope everyone's really excited to get this all started. So, like, when we go back to last year in Grakn Cosmos, we were completely mind blown when we learned about all the kind of things that people were developing with Grakn and the people that showed up at Grakn Cosmos. It was truly inspiring for us. We learned so many things about the use cases of Grakn, which we didn't even imagine. Now, there is one important thing, though, that we learned that is really, really critical, is the fact that at that point, we also learned that we needed to solve the performance of Grakn to really take everyone in the community to the next level, to production, to scale, and beyond. And so that was basically our ultimate goal of 2020, no excuses, right? And so we start, in this talk, we start from what we had last year, where we started last year in terms of the architecture that Grakn has, and I'm going to tell you a whole journey of what actually happened over the past year and why most of us went silent to the people in the community, to our families, to our friends, and just kept our heads down and just coded throughout the whole year. And so ultimately, the performance that we knew we had to basically fix with Grakn hinged on the fact that Janus Graph was not the most optimal solution as our database, as our technology, as our database the back end of our database technology. And we knew all along that when we needed to basically optimize the performance of Grakn, we would start there, right? Now, the problem is that there's a lot of things sitting on top of Janus Graph. So first of all, Janus Graph sits on top of a backend storage. There was multiple options. We chose Cassandra as Janus Graph's backend storage. But then on top of Janus Graph, there's Tinkerpop and Gremlin, which is the graph query language that we use to query Janus Graph. And then there's Spark, that provided us the Prega libraries for us to be able to perform analytics. And then everything else that we built in Grakn, so the knowledge representation system sits on top of all of that. And then the analytics and reasoner sits on top of the knowledge representation system. And so does the query engine, which taps straight directly into Tinkerpop as well. And then there's the RPC server serving the database over gRPC. Now, we thought, okay, let's start refactoring. That's where we started. We were quite reasonable in the beginning. Now, when we opened the bonnet, we realized the amount of complexity that Janus Graph's code base had was basically beyond what we thought we could basically refactor in time, because the point of Janus Graph is that they're highly interoperable. They have a lot of different backends that you can choose to basically persist your data for Janus Graph, and that interoperability basically created a lot more feature and a lot more code that we actually needed inside Janus Graph, and untangling it wasn't really a task that was feasible. And so we thought, you know what? Let's build our own graph storage engine and define it as we need, tailored to our own data structures, and this would allow us to give the full control and freedom going forward to make it as performant as we want in the way that we want it. And so if we're going to rewrite a new graph storage engine, so we might as well ask, what should be the backend of this graph storage, right? Should it still be Cassandra? And quickly we realized through very brief, thorough, but very quickly when you start researching in this space, you realize that RocksDB is the best option as a key value pair storage, right? It's written in C, it's highly optimized for storage, flash storage, and RAM, and it's as low level as simply key value pairs of byte arrays, right? Of byte array streams. Now, the proven scalability that the Facebook engineering team has basically shown with RocksDB was beyond what we needed for our confidence. So we went with that. And we built our own graph storage engine on top of it. We built two graphs, actually. There was a type graph and a thin graph. Both of them are normal, directed, normal in the sense that it's a directed binary graph, but it's tailored to our own hypergraph data structure. So it's not quite general purpose, right? Now, this means, unfortunately, Spark no longer runs on top of our graph storage engine, because Spark was running on top of Janus Graph through Tinkerpop at that point. And so that means, that last year we had to sacrifice analytics, for now, at the very least, right? We do intend to basically bring it back in once we basically get our architecture, the new architecture done right. So for now, it had to go. right? The next thing we did when we realized now we have a truly optimized graph to our own data structure, we took our knowledge representation system and we built a whole new version of it, which we consider as our own type system, right? It's a logical system that imposes a set of rules that governs a program. That's what a type system is. In our case, it governs the types of your schema, the types of data that you can insert, the query that you write onto the database, and whether it's valid or not, and ultimately it encodes the logical representation of the data for the purpose of logical interpretation by the reasoner, right? And the Traversal Engine. So we're gonna really drill into this in this talk a bit later. But then after that, which took the most amount of time for us, we went on to build our own Traversal Engine that replaced Tinkerpop. Because again, because we have our own data structures optimized in the graph that we've built, it made sense for us to build a Traversal Engine that was natively parallelized from the get-go, right? And what it basically opened us to the opportunity that it created for us is that now we can build our own query optimizer, which is based on the Traversal Engine and leverages the information from the type system, right? And this is based on mathematical optimization / integer linear programming, if some of you are familiar from that space. And so we can leverage a field that has decades of research on how to optimize traversal paths that we haven't been able to do before in Grakn, right? And then on top of that came the whole new reasoner architecture that is based on the actor model, which Joshua will go deep in his talk tomorrow. And this basically gave a whole new distributed architecture to our reasoning engine and taken it to, again, to the next level. Finally, we got to the RPC server. Even the RPC server had a lot of room for optimization, and that was how can we create a server that streams data from the server to the client continuously, but without bombarding the client and without killing the server. So there has to be a mechanism of control, of flow control on how the information gets passed from the server to the client. So in other words, we need some form of back pressure, right? So continuous streaming of data with some form of back pressure. We want it to be non-blocking. Sounds familiar? That's effectively the reactive stream model, right? That's a reactive stream pattern that we want to now adopt. And so we re-architected the RPC server to do that. And at that point last year, we only had Java, Python, and Node.js as the primary clients that you can basically use to talk to Grakn. But now we know that there's Julia, Go, C#, Ruby, and Rust client developments in the community that is ongoing right now. So that's another thing that's truly exciting about this new architecture. So, of course, this is now the Grakn 2.0 architecture, right? And it looks similar, but it looks exactly the same, but at the same time completely different, because everything from ground up has been completely rewritten. And so that was literally the madness of 2020 for most of us. We managed to release the alpha in like 13th of January, and we've released like 9 alphas since then, and production release happened on 31st of March. So that was one hell of a year that I think I'm going to share even more sometime in the future as to the journey of that in and of itself. But for now, of course, you're wondering how much better is this code base over the old one, right? How much better is 2.0 over all the 1.1, 1.2, 1.3 to 1.8, right? So, like at top line figures, right? For example, for write performance, for 32 million SQL records, that used to take 5 hours on the old 1.8, right? In the new 2.0, that takes under 5 minutes, right? Of course, this is being loaded on a 72-core machine, but even on a 72-core machine for 1.8, we weren't able to exploit the CPU cores to actually to properly vertically scale at that point. So now we can, and this is among the top line figure of the amount of writes that you can, the highest burst rate that you can basically ingest into Grakn. In terms of reads, so common read queries, so like as in by common as in like not like hugely long, like 15 relationship queries. The common relationship queries the common queries in Grakn we've seen improve from what used to be 150 milliseconds to 6 seconds now falls in the range of 10 milliseconds to 50 milliseconds, right? Now, all of this is hugely predicated on the fact that there's like, I mean, there's a lot of things in terms of algorithms and data structures, of course, but one of the really outstanding figure of what changed in the architecture is that back in 1.x, right, we used to be able to only utilize 50% of a 16-core machine, and it didn't really go up any higher than that. And in 2.0, we've tested that. We don't know what the maximum is yet because, I mean, in the cloud provider that we're using right now, 72 cores was basically the biggest VM, and we know that we're utilizing 98% of that 72 cores. So for all we know, we could be testing it on a higher number, and it could still be maintaining that rate. In any case, we knew at that point we were happy with the figure and we kind of stopped testing it. Now, this basically puts the top line improvement around 60x on data ingestion rate, and 3x to 120x on read performance, and 9x and probably even more on CPU utilization of the machine. So, like this is something, of course, hugely rewarding for us to find out that this was basically the outcome of the complete rewrite from ground up for us, which, of course, from the start, of course, we believed that that was going to happen, but you don't really feel it until you really see the numbers, right? So, I'm not actually going to share the comparative benchmark yet in this talk right now, but I'm going to basically let you guys take a peek right now on the starting of a benchmarking project that we're doing against Grakn 2.0 and Neo4j, and we're going to be benchmarking against many other databases too, not just Neo4j. It's just, this is like one of the most common questions that people ask, right? So basically, imagine that there is a simulation system that runs like multiple agents per iteration, right? Without getting into too much detail of that. And there's an agent that basically gives birth to people. It creates people in the database, right? And let's say it does so by picking, so like there's an agent that operates at the country level, right? It picks a random city, and then it inserts a person that basically has a random email with a random name, a random address, random gender, random birth date, right? So each agent at which there's one per country, does 10 of these queries. And then there's 250 agents concurrently, right? And that's in one iteration, and we run it over 100 iterations, right? And the query does exactly the same thing on both Grakn and Neo4j. What we found is that Grakn's performance is constantly stable throughout all of the iterations, and we perform roughly around 5 to 8 times faster than Neo4j. Now, there's a lot of ways, there's a lot of angles to cover, there's a lot of there's a lot of cases to cover in a comparative benchmark, and we're going to do an even more thorough study before we publish the full figures, but we are already working on it right now, and we'll be sharing more about this after Orbit. Now, all of this is exciting, of course, right? But it's the evolution of the architecture, the evolution of the database, and the evolution of the performance isn't quite the biggest thing that we want to share, that I want to share with you today, right? So what is the biggest evolution of Grakn that happened over the past year because of the rewrite, right? And this is the thing that is a huge shift to the trajectory of our work, because what ultimately evolved was our understanding of our own work, our understanding of the technology and how it sits relative to the industry, right? Our understanding of what the technology does and how it serves the applications on top of it. And I know it sounds all too philosophical, but I suppose when you're deleting your work for the past 5 years and restarting it from scratch, I think getting a higher level overview of the entire journey and the entire architecture is probably inevitable. And so that's what happened basically with us. Now, to tell you this evolution, basically we need to reassess and recapture the truest essence of what Grakn is about. The key pillars, the key value propositions, if you may, right? What makes Grakn, what makes the database that we build unique? What makes it novel? What is it about it that defines its characteristics, right? And so we started basically, again, reassessing our work through the code that we've written for the past year, because, and it wasn't actually, it's not just the fact that Grakn is a graph database. We actually been trying to correct people about that for many years, and since the beginning, that Grakn isn't merely just a graph database. Yes, you can see it as a knowledge graph, but again, it's not only beneficial for people in the graph space or the reasoning space, it's beneficial for people coming from SQL, from Mongo. And the reason is because there's an overarching philosophy that Grakn is basically trying to fulfill. And so, and that was reflected from the fact that it took us roughly 6 to 8 weeks to build the graph storage engine. That was all, right? Why the hell were we late for the delivery, and what have we been doing for the whole year, right? That's basically everything else around it that basically made Grakn truly unique. And what were those things, right? So the first thing we realized that is the biggest pillar of Grakn as a database is the expressivity, right? Now, some of you may already be familiar with this knowledge model, which was presented last year at Grakn Cosmos. But we're not going to try to decode it today, even though this basically captures the essence of what you can do with Grakn, but it's not quite helpful, especially if you're new to Grakn. Let's peel it one layer at a time through an example, right? So, for many of you, maybe this is the first time that you're looking at the Grakn, the Grakl language, a Grakl schema that you write to define the types in Grakn, right? So I'm going to briefly, so many of you from the community obviously would already be familiar to this, so bear with us for a little bit. Right, so like in this brief snippet, short snippet of code, you are looking at 90% of the keywords of Grakn, right? So person, sub-entity, company, sub-entity, employment, sub-relation, and a name sub-attribute. Entity, relation, attribute, right? And if you're familiar with the ER model, the ER diagram of SQL, the entity relational model, like you would already be familiar with these terms, an entity, a relation, an attribute, right? Now, what we're introducing is the fact that there are roles. So you can see in employment relates employee and employer. Those are role types, right? And person plays employee, company plays employer, right? So that's, like with these keywords, you can model a lot in Grakn, right? So I can't basically see people's faces nodding right now. I can't see if you're frowning or smiling, so I'm going to assume that you get what I just said, right? So I'm going to assume that this is simple enough for people to be able to move forward from this page. And so what I want to point here, which is interesting, is the fact that company owns name and person also owns name, right? So the attribute is shared between two entities, right? So many of you who are familiar with database theory, you'll realize that this is actually a representation of first normal form, right? Where a relation is in first normal form if the domain of each attribute contains only atomic values, right? And the value of each attribute contains only a single value from that domain, right? And so this is a key piece of our modeling philosophy because this allows you to stay really, really high level in your modeling system, right? So let's extend it a little bit, right? Let's say we have subtypes, we introduce subtypes, right? So not just person sub-entity, but now a customer is a subtype of a person, right? So this means that a customer inherits everything that a person has. A customer also owns a name, a customer can also play the role of an employee in an employment, but additionally it has an attribute rating, right? How you think in OOP, object-oriented, and how you would basically inherit properties from classes that you extend, this is very, very similar, almost identical, right? So at this point, I trust that the code is making sense already to people. I'm not going to rely on the code going forward too much because the graph on the left-hand side is already a representation of what the code is writing, and I'm going to speed through the models that what else can we do with this system, with this modeling system, with this language, right? So let's say we extend it a little bit. Here we have marriage, which also has two roles, wife and husband, and a person can play both wife and husband, right? So let's take a look at how would you write data for this, right? How would you actually insert data that matches that model? This is how you would write data, right? $A is a company, has name IBM, $B is a person, has name Alice, and AB is an employment, so they're in an employment relationship. And a startup, Grakn, and a customer, Bob, they're also in an employment relationship. Can a startup employ a customer, right? Can a customer be married to a person. So wife B, husband D is a marriage, right? So we're going to talk more about that later as well. But I want to give a quick intro of basically how you would write a query representing the structure that you want to query, that you want to ask on the left, right? Now, we've seen a simple query, we've seen a simple schema, right? But what else do we mean by expressivity, right? The type inheritance, which you saw a snippet of just now, can go beyond just one level. It can go as extensive as you want it to be. And it doesn't actually just bound you to create type inheritance from entities, but also from relation types. So for example, yes, relation types can be subtyped. So let's say an employment relationship, right, between a company and a person can be subtyped into a temporary employment or a permanent employment, right? And of course, there's like, we saw a snippet of it in the previous page as well, where we can inherit attributes and role types, right? We can also override them. I'm not showing them in this example right now, so you'll have to take my word for that. But the type inheritance is a full-blown OOP model of what you can present in the database, right? Now, it doesn't actually stop there in terms of a type system, right? What else can you model? There's actually a lot of different types of relationships in the real world that you need to be able to model that is not quite natural to current databases. For example, you want to model reflexive relations when a person is related to another person, or a symmetric relation, right? When A is married to B, B is also married to A, right? In a graph database, you'll have to basically point one direction. On which direction are you going to point it to, right? For the husband to the wife to the husband, or from one spouse to the other. But how do you query the other side, which is not going to be the same query to query from the other side, even though the meaning is the same, right? And then there's transitive relations, where a relationship can be composed of other relationship that carries the same semantic as the initial one. There's ternary relations, where there's 3 role players in the relationship. But what if there's just an arbitrary number of role players, right? Let's say a joint venture of multiple companies, like joined into one, right? So there's multiple owners, and you don't know what the number of role players actually are. So it's just infinity for all you know, right? And then there's nested relations, right? Let's say you have a marriage between like A and B, and then that marriage is also within another relation. So that marriage is located in a city, for example, right? And then you want to, let's say you want to encode equivalent relations. So one relationship structure may be equal to a different relationship structure. So this is going to be encoded via rules, which I'll show you more of the effect of it later, and also what Joshua's going to be drilling into further in his talk, right? Now, what does all of this basically mean? All of the different types we can represent, the relationships we can represent. The point of it all is that with the type system that we have, the database allows programmers to think much, much higher level, right? You don't think in join tables, columns, vertices, edges, properties, second normal form, third normal form, fourth normal form, normalization, this, normalization, that. You simply think at the conceptual level how you would represent the world in your mind, and you model it as is in the database, right? Thinking higher level because of the model allowing you to encode it so, right? That's what we mean by expressivity, right? The second one is safety, right? This is what we found out to be the pillar of Grakn that was hugely, hugely underrepresented last year and the years before, but it makes up a huge amount of our code base, right? It makes up a huge part of our work. And what do we mean by that, right? So let's take the previous example of a schema that we've already shown just now, right? And let's say, so let's remember this schema is the restriction of what our database allows us to do, right? So a company owns a name, person owns a name, and a company plays a role as employer. In an employment relationship, person plays a role as an employee, right? And then startup and customer, subtypes person, company and person, right? And then there's a marriage relationship between people. So let's say we want to insert data, right? That basically says, all right, cool, I want to insert, this is the previous query that we had, right? Insert like the company IBM, married to, like employing Alice, that's straightforward. Obviously that's allowed, right? What about startup employing a customer, right? That's not obvious from the previous schema, right? At commit time, this will succeed. Reason being is because a type validation can derive what is logically permissible by the schema, even though it wasn't explicitly defined yet. So yes, there are schema constraints that exist in SQL and other databases, but the distinction here is the logical derivation of what is permissible beyond what was explicitly defined, right? Now, so that's what exactly. So that's an example of a more advanced evaluation of a correct query, right? But let's say you write something that says, you know, a person, Charlie, married to a company, Apple, right? So at least in our world, in the schema that we wrote, that was not allowed, right? So this is beyond just checking whether a string is allowed to be passed to a double, or a double being passed along to an int, or whether a double can be passed can be used as a key. This is validation of structure, whether what we are inserting to the database actually has meaning structurally, logically, right? And this doesn't. This will be caught by the type validation, and the commit will fail, right? And so we are protected from data that doesn't have meaning, data that is invalid going into the database, right? What about data going out of the database? Let's say we want to do a query that says, Alice, look for a person, Alice, that employs another person called Bob, right? Still given the schema that we showed 4 slides ago, right? And now we want to ask, like, so Alice employing Bob, and Bob being married to Oracle, for example, right? And we know from the previous schema that this makes no sense at all, right? But in most databases, you'll be fine. Basically, just query, and you'll get an empty set, right? The problem with an empty set is that an empty set is a valid answer to a query in the database. An empty set basically means this thing doesn't exist in the database, right? But it doesn't tell you that actually your query is wrong. It has no meaning. It has no meaning in the universe that you've defined, the domain that you've defined for the database, right? And in Grakn, in 2.0 especially now, there's a type resolution component that will kick in, validating your query and make sure that it makes sense at all. Even if it doesn't make sense at all, like what you see in here, an exception will be thrown. So instead of basically just getting an empty set, we're going to give you a small slap on the wrist telling you that your query doesn't make sense, right? So you don't proceed going forward thinking that, like, oh, I've checked the database, it doesn't actually exist, not knowing that actually your query is wrong altogether, right? So the ultimate benefit of this, we realize, putting them all together, is that with a type system sitting in a database, a type system as advanced as the one that we've built, it allows us to detect meaningless and invalid queries. And ultimately, what that means is that you have data that you can trust, you can more trust than what you had before, because you're not just relying on programmers. And of course, we all trust the programmers writing the code and writing the data into the database. But again, we're humans and we're going to make mistakes. And if there's that logical barrier that basically protects us from the mistakes that we're going to be making, that's a really, really, really critical distinction, a critical functionality that the database provides to the application sitting on top of it. And so that was the second pillar that we realized about Grakn, right? The third thing is the popular pillar that everyone already knows, is inference, right? What do we mean by inference, right? So many of you probably have seen this example before, but again, to basically to remind ourselves of it, and also to introduce it to many people who are learning about Grakn for the first time right now. Let's say you have, like, this is the kind of data that you have sitting in your database, right? There's company data, charity data, university data, and any one of them can be connected to an office or laboratory or a warehouse, and any one of them can be connected to a location, like King's Cross or London or the UK. And these types of locations aren't like of the same type. Like King's Cross is a I think a suburb in London, and London is a city, and the UK is a country. So they're all of different types. And so if you want to perform a query that looks for finding organizations that can, no space in memory card. Okay, sorry. And you want to perform a query that looks for organizations that have premises in the UK, the queries that you're going to write is going to be highly primitive. So, and it's going to be really complex. And so while the data that actually exists in the database, let's say it only looks like this, but you don't know that ahead of time. So how can you write a very specific query looking just for the structure that actually exists in the database? You can't, right? So with Grakn, you would write a higher level query, right? Something that looks like this. So like we were going to assume that company, charity, and university are subtypes of organizations in Grakn, and office, laboratory, and warehouse are subtypes of premise, right? And King's Cross, London will have located relationships into London. And the query will be a simple 5 lines asking for match OR is an organization, PR is a premise, UK is a country, has name UK, and OR PR is in an ownership relationship, PR UK is in a locates relationship. What's happening here is that the organization, the OR PR and OR PR relationship are actually parts of the query that will be performing type inference, because it will derive all of the different subtypes that it has and what are the permissible combinations that actually exist in the database, right? And the very last one, PR, so a premise that is located in the UK, will trigger a rule inference, right? And they both work transparently in tandem when you perform the query, right? And so this simplifies the initial query that would have been extremely complex for the developer to write, because we now just get to write the higher level abstraction of it. Now, of course, we ask, you know, how representative is this query to the query in the real world that you'll actually be doing, right? Now, in one of the talks that Thomas gave last year in Grakn Cosmos on the comparison of Grakn to SQL, he gave a talk on this, and you can find that talk to find the elaboration of this. But this was a real query on a project that he was doing on a biological network / disease data that was basically captured in Grakn. And the initial data source was from SQL, and that was this SQL query that they were having, right? And after modeling the schema, the roles, the data all in Grakn, in the end, the final query that they needed to write to query the database on Grakn was a simple 3 lines, right? Of course, these 3 lines basically trigger a series of type inference and rule inference that expands even further. But the point is that like all of those things happen once, written once, and reused many times by the analysts, the biotechnicians that were querying the database, right? And that reusability of the abstractions, because of the abstractions of the complex components in the data model, in the data set, is what boosts the productivity of people working on the database, right? So the type and rule inference basically provides a layer of abstraction of complex data patterns to its logical equivalent. So ultimately what we learned here is that because of the type system that we have, the database is able to encode the domain for logical interpretation by the reasoner. And this allows us to perform type inference and rule inference that creates logical abstractions of data, right? Not basically the essence of what we see is happening in inference. Now, on the last, not least optimization, right? Now, this is the work on optimization right now is still very much in its infancy, but it's completely novel. It's a novel approach that we've never taken before, based on the field of mathematical optimization / integer linear programming. And so, like, I'm not going to actually get into the math today, but I'm going to give a quick, like, cursory glance of what the problem actually looks like, right? So let's say we have a very simple query, right? A is a person, B is also a person, and A is married. Yeah, A is married to B, and B is employed by a company, right? And we want to find the person and the company that employs their spouse, basically. How would we go about executing this? If we start the query from person to A to B to C, right? And it turns out the database has 1 million instances of person and 10 instances of a company, right? And let's say 60% of the people are married, right? And these 10 instances of the company on average have 30 employees in your database, right? The outcome of this means is that the maximum traversals that will be created will be up to 1 million traversals, which is where you started off at, right? The number of instances of people. Now, the likely number of traversals that will exist, based on the structure that we have here, is only going to be 180 traversals. That's 0.018% of the total search space, right? Now, let's say we reverse the query, right? Reverse the execution. We start from company instead, right? And then to person, and then to their spouse. The search space, the maximum number of traversals created will only be 300 traversals. The number of likely traversals successful will be the same, right? But now the results is 60% of the search space, right? So optimization is about reducing that search space to the minimum such that every second, every minute that the CPU performs computation, you get a result back. That's how you speed up getting the answers, right? So now, of course, like the real optimizer look nothing like this, right? The real optimizer for this two simple queries will have 44 constraint variables, 52 constraint equations for one goal function, right? And like, like so queries with like in like multi-hop queries can easily get up to like thousands of variables, and that is what these mathematical solvers are already quite mature to optimize. And we're not going to go into the math, but what we can see here is that the information about the type, about the relationships, about how many are related, what's the average number of relationship between two types, all of these information is what informs the optimizer, right? So that's what, that's how the optimizer can then prune the search space. Now, of course, like how hard is that problem anyways, we think, right? It's only in this two-hop relationship. Of course, the two-hop query, this may look trivial to us, but what if this is a query that is actually from a real project that we know is going on, and the question is basically to get me proteins and genes connected to tissues affected by diseases in the category of cancer, right? This could easily go up to thousands of variables, and for non-declarative languages, if the developers have to basically determine the executional path, the effort to find what is the most optimal path to query the graph will be close to impossible. It will be really hard. At the very least, we can say it would be unproductive, right? Especially if you do have to do that for every query. So what we've learned now, what we can do is, because we have a type system that is very extensive and allows us to capture metadata about every type of data, right? We're able to feed this information into the query planner and trim down the search space exponentially, right? So this is still very much early days, but for us right now, we've proven the hypothesis that it works, and we're going to be continuing iterating on it much, much further from this point onwards. But ultimately, what we've learned is that because of the type system, right, our database is able to provide more information to the query planner such that the query planner can perform a global optimization to find the most efficient path, right? And this is something that is going to be really fundamental in the work that we're going to be doing going forward, and we're going to be putting in a lot of effort to continue improving the optimizer inside Grakn. Now, those 4 pillars that we now see Grakn, we now see frontline as the key characteristics of Grakn, beyond the fact that Grakn can store a graph, beyond the fact that Grakn inherently can be used as a knowledge graph, beyond just the inference functionality of Grakn, those are the 4 pillars, right? They were expressivity, safety, inference, optimization, right? No, it's not about vertices, it's not about edges, right? It's not about tables, it's not about joint tables, it's not about graph databases, right? It's about expressivity, safety, inference, and optimization, right? Now, what do all these 4 components share in common, right? What do they all share in common? And I think at this point it's obvious to us that it's the type system that we've built, what was previously our knowledge representation system, right? What was previously our knowledge representation system is now simply our type system in Grakn. And why is this special? Why is the type system such a critical component that we want to put at the front line as the key philosophy of what Grakn is all about? That's because fundamentally, a type system is built to address the problem of ensuring programs have meaning. And this has been driving the evolution of programming languages for decades. This is how languages evolved from C to C++ and Rust, how JavaScript evolved to TypeScript, right? And Java with its OOP and generics functionalities. This is how programming languages evolve. They build a more advanced type system to create more meaning in the programs. Now, we realize that actually, it's not just programming languages that can leverage the benefit of having a type system, because the notion of creating meaning in the program is completely lendable to databases having a type system to create meaning in the data, right? But you say, why is that new? Why is that important? I mean, SQL has a type system, right? Well, if you think SQL has a type system, well, then by that logic, which is true, right? But if you think that's completely comparable, then you think, then we can also say that like C and C++ and Rust are all comparable because they all have type systems too. C, even as early as C, also has a type system, right? Now, the key point is that type systems aren't quite, the effect of what a type system does isn't quite binary, right? The more expressions and restrictions that are imposed by a type system, the more strongly typed a program is, right? And that's why we can see that in C++, with the notion of classes and object-oriented programming that C++ introduces, it's a lot more expressive and restrictive than C, right? And that's why we can see when we compare Rust to C++, it has more expressions and restrictions that governs the program control flow, right, of objects in Rust is superior to what C++ has, right? So when we look back at Grakn, right, does it have more, does Grakn's type system provide more expressions and restrictions such that it is a more strongly typed program too, right? Well, if we look at the expressivity, Grakn provides a much richer data structure, right? More higher level, more expressive, and we've seen all the examples. And in terms of safety, we guarantee more meaningful input and output. We perform logical verification rather than just static and explicit verification. In terms of inference, we provide a whole new level of logical abstractions of data. In terms of optimization, the type system provides more information to the query planner to find the most efficient path of execution for the query, right? So I think at this point, it's fair to say that we think Grakn is a strongly typed database. And Grakl is its query language, right? Now, when we think of it that way, we realize, is Grakn still the right name for us to present the work? Is it still the right name to represent the technology that we're building? I mean, let's also be honest that most of us sometimes get it, like don't really know how to spell Grakn, not at least the first time. But putting that aside, right? There is this notion, this air of association of Grakn to the graph world, especially probably because of the word GRA in front of it and Grakn itself standing for a graph of knowledge. And yet we've established that it's so much more than that. So doesn't it deserve a name that is more representative to what it's about? Maybe we should call it something else. It's a strongly typed database, so maybe we should call it TypeDB. And the language is TypeQL. TypeDB is a strongly typed database. And TypeQL is a query language, right? And that is how I want to, and that is how we want to capture the biggest evolution of the technology and the work that we've been doing for the past year, is to present to you a new way to see Grakn, a new way to see the database. A database which would probably be more appropriate to be called TypeDB. And the language is TypeQL. And that is how I want to introduce to you TypeDB. Now, of course, as a final note, like given that the database is no longer called Grakn, it doesn't make sense for the company to be called Grakn Labs. Now, the story of how we found the name is another story for another day, but at this point, I want to introduce to you the new name of our company, which is Vaticle. And so, the database is Vaticle TypeDB. And with that, I want to end my talk, and I want to wish you all the most amount of fun in this conference and learn the most that you will over the next 2 days. And I look forward to answering all the questions. I look forward to hearing all the talks from the community members and learning about what everyone's been up to for the past year. I want to thank you all for tuning in. Thank you. Thank you, everyone. Bye.